Well, welcome everyone to today's AllTranstek and FTR webinar titled Non-Destructive Testing 101. I'm Eric Starks, Chairman and CEO with FTR, and I will be your moderator for today's webinar. We are delighted to be able to bring you this event. As a bit of house cleaning, I want to let you know that there will be a webinar replay available by this Friday. An email reminder will be sent once this replay has been posted. Now, the format for today's webinar will be formal remarks from our speaker. This will then be followed by a question and answer session. The length of this webinar is scheduled for 1 hour. All of the formal remarks should be completed within 45 minutes. So this should allow us about approximately 15 minutes of Q&A. So let's move on to the formal presentation. Joining me today is the distinguished Jim Donnell. Jim is Vice President of NDT and Special Processes. He has been with the industry for over 30 years and is highly recognized within this sector. So, Jim, I would like to welcome you to today's event, and we appreciate your insights. So, welcome, Jim.
Thank you. Hello, everybody. Hope everybody can hear me. I'm just going to try to go back to my... Here's our team.
Well, here we go. Okay.
Okay, here we go. Sorry about that.
Sorry about that. Yeah. No, we're good, man. We're good. Let's have some fun. Here we go.
Okay. This is kind of our team here. I just want to kind of get into NDT 101. So, what is non-destructive testing? Sometimes called NDT or NDE or NDI, or non-destructive examination or non-destructive inspection. Really all the same thing. So, NDT is just an acronym for non-destructive testing. It's a group of well-developed processes that aid in assessing the quality of the component, hopefully without hurting it apart in any way. Many times, a proper non-destructive testing program, only receives attention, kind of when it's too late, and that's something that we try to avoid. So really today, I'm going to talk about, and there's many types of non-destructive testing methods, and within every method, there's other separate techniques. So I'm just going to kind of go over the more common ones that we use, and I'm just going to kind of review some of the advantages and limitations of each one, because they all have advantages and each one has their limitations. So I'm going to talk a little bit about visual inspection, penetrant magnetic particle, a little bit about radiography, leak testing, ultrasonics, and just briefly on some thermography. Some misconceptions about NDT is viewed kind of like a knight in shining armor that will compensate for design and workmanship issues, and it will not. Non-destructive testing is viewed as a cost and not as a risk reducer. I like to look at it as a reducer of risk. And non-destructive testing sometimes is viewed as 100% effective. In other words, many times people will say, if I inspected it and it's good to go, there's no defects in there I have to worry about. And that's just not true. They may be only 80 to 85% effective at locating flaws at best. Now that's, that may sound bad, but it's really not it. It's just how you use the method mainly. NDT is a useful tool that can assess the quality of a part, but it depends upon the following: qualified personnel, qualified procedures, and proper acceptance criteria. In other words, telling the inspector what is good and what is not good or a defect. Properly performed and proactive, NDT can be extremely cost effective when considering the other possibilities. So I really broke this into kind of 3 parts. Part 1, we're going to talk about some basic methods and their advantages and limitations. So the first one I'll talk about is weld inspection. Weld inspection, or visual inspection, is the most common and probably the most used non-destructive testing of all the methods. Because most things are going to have to pass some sort of visual inspection before you proceed with a more detailed other non-destructive test. There's several tools that can be used to inspect various types of weld joints. Many times, if you're doing weld inspection, after it's been welded, you're just kind of looking at the tip of the iceberg in some ways, but there's still many things you can inspect visually. Your filler weld gauge, to measure the length of convex welds, you have to have the proper gauge to measure the different types of dimensions on a filler weld. One thing about visual testing on a weld, the weld itself may have no defects in it, but it still may not be good depending on the size of the weld. The weld drawing might call out for a certain size weld, and even though it has no visual defects in it, it's undersized or can be even oversized. So there's many things you do inspect visually. The next thing I'll talk a little bit about is magnetic particle testing. Now with mag particle testing, there's several different techniques within mag particle that are very different than each other. They all use magnetism, but what I have on the screen here kind of shows you just two different techniques. One on the left is the magnetic yoke method, kind of like using a horseshoe magnet. One on the right is what they call like a wet horizontal bench technique, where the parts put into this bench and magnetized, obviously for smaller parts. So not to get too much into magnetic theory, but if you see on the bottom left, you see a bar magnet, and you know it has a north and south pole. Inside that bar magnet, you have these lines of flux, or these flux lines that are running through the part. You can't see them, but they escape out of the north and south pole. They are there. So what you see on the top left is a part that's been magnetized, and these lines of flux, or these magnetic lines, are running through the part. And just like water going down a stream, if they hit something and they can't go around it, they will actually jump out of the part. As we see here is what we call flux leakage, where the flux lines run through the part and then they can't get around the part and they actually escape. So what you have here is like a new north and south pole. And there on the bottom kind of shows you a yoke, what they call magnetic yoke, used on a car. So kind of getting into more of the flux lines. The forces that attract magnetized poles is known as magnetic flux. Here we kind of show you a horseshoe magnet. That would be like a magnetic yoke. If you put the part or the yoke on the part, the magnetic flux lines will actually enter the part. And then what we do is we look for those flux leakages, areas where we have new north and south poles. And if you have any kind of crack that's open to the surface or very close to the surface, they'll have flux leakages there. And if you put some iron powder that maybe has a dye on it, they will be attracted to those areas. Magnetic particle buildup. This sketch shows the buildup of magnetic part medium over the discontinuity in a magnetized part. You kind of see the new north and south pole right here, and we have some iron powder. In this case, it's colored red. We just spray or actually apply the powder over the part, and if there is a north and south pole there, if there's a magnetic area there, it'll be attracted to the part. You know, magnetic part testing is relatively easy. Simple test method that can be applied at various stages of manufacturing and processing. Some advantages of mag particle: it's really good for surface flaw. Really, of all those methods I showed earlier that we're going to talk about, this may be the best overall for looking for surface cracks. At least we run side-by-side tests with some of the other methods. It's really good for surface cracks. It's quick and reliable test method. It's done very fast. It doesn't have a lot of training involved, It's a very quick and easy method. So it does have a lot of advantages. Many companies like using it, but it does have some limitations. It's limited to magnetic materials. So if you have a car that's non-magnetic, a stainless steel, aluminum, tank car, obviously it can't be used. It cannot really locate really internal discontinuities, just like visual. You're really looking at defects that are open to the surface. And residual magnetism can affect future processing of the part. So sometimes if you magnetize something and it has to be welded afterwards, you'd want to demagnetize it because sometimes it will stay magnetized. This is kind of a good picture of, sorry about that, it jumped. What you see here on the left is a part. Now you can't see the crack at that hole, but after we applied mag powder, magnetized it, we applied mag powder to it, and you see there's actually a crack emanating from the radius of both sides of the hole. Next thing we'll talk about is liquid penetrant testing. Probably one of the older methods used many years ago, sometimes called dye check, dye penetrant testing. Here we see some typical equipment used with liquid penetrant. So with liquid penetrant, some of the basics is that penetrant testing is a method that locates surface discontinuities. One thing about penetrant testing is that if you're looking for the discontinuity, it has to be open to the surface to allow penetrant to enter the part or enter the defect. In the liquid penetrant method, the liquid is applied to the surface of the specimen and is allowed to penetrate the surface discontinuities. And it doesn't just kind of enter it through gravity, it's actually sucked in the penetrant. And I don't want to get too much into capillary or capillary action, but it's a phenomenon of nature of hydrostatic law that liquid will seek its own level. If you ever had a very small glass that had water in it, you will notice that at the sides of the glass you may see water come up both sides of the glass as through surface tension. And we can use this, what they call adhesion and cohesion, in our liquid penetrant method. It will actually, so if you get something that's very narrow, like a crack, liquids will have a tendency to want to get sucked into the narrow opening. So you can do penetrant testing overhead. It has nothing to do with gravity as far as penetrant getting into the part. So you can take any type of liquid, have any type of dye in it. Usually it's going to be something like red, something that stands out. You put penetrant on the part, and after sufficient time dwell time has passed, you take the penetrant to enter the discontinuity of the surface of the part is cleaned. Then we use capillary action again, is employed by adding a developer to draw the penetrant from the discontinuity. You see here on the left this is actually a bar termination here, where we've had cracks right in the tank shell here, and you have bleed out. So when you have the white developer over it, the red stands out, and it makes something that I guarantee you probably wouldn't see visually, and it makes it much more visible after penetrant is applied. As far as liquid penetrant testing can be used on a wide variety of materials. One thing about penetrant over magnetic particle is it can be on ferrous parts, in other words, magnetic parts, non-magnetic parts, like aluminum, brass, glass, ceramic, plastics. You can do penetrant testing on a lot of types of materials. But the only type of material you probably don't want to use it on would be something like a spongy material, be like something like pottery that's unglazed, because then what happens is the dye just gets sucked into all the little holes and everything bleeds out when you put the developer on. You can't tell the defect from a non-defective area. I love sponge bond. So I'm going to kind of walk through this process of penetrant. Here we have two plates, and these plates have some flaws in them that I guarantee you couldn't see visually. And we're going to run through the penetrant process real quick. First thing we would do is clean the part. Very good. Then we're going to apply our penetrant. In this instance, we're going to apply a red dye. And when we're done, you see the red dye is applied over the weld, and you're going to probably want to follow the procedure, but you're going to put penetrant on the weld itself and probably either side of the weld to look for defects in what we call the heat affected zone. So after you apply the penetrant, you have to wait a certain amount of time because it doesn't happen very quick, and that's one of the disadvantages of penetrant. It's a very slow, methodical process. So you may have to wait something like 10 minutes or more to let the penetrant enter the discontinuities, possible discontinuities. Then you're going to clean all the penetrant off the best you can off the surface. And you can use a cleaner for that. Keep wiping, and you keep wiping. It's a very slow process. Then, after time has elapsed, then you're going to add what they call like a developer, and it's going to be like a white powder that's in some sort of vehicle, like a alcohol-based vehicle that dries. And it's no different than you would, like a Bounty paper towel. Any kind of penetrant that's still in that crack is going to be blotted out into the white developer. And then what you're going to get is a bleed out from a possible here where it looks like a toe crack in the toe of the weld. And you can see how much wider it bleeds out after the penetrant comes out and bleeds over to the developer, making it very much visible. So great method, very methodical, very slow, but very tried and true. So as far as advantages, relatively inexpensive compared to magnetic particle. The penetrant material, there really doesn't cost all that much other than some penetrant material, rags, and things like that. Liquid penetrant testing can quickly examine all the accessible faces of an object. So complex part and complex shapes really doesn't really hurt penetrant testing. And liquid penetrant testing can be used on a wide variety of materials like I already talked about, ferrous, non-ferrous, metals, and glass, and such. But it does have some very major disadvantages or limitations. Limitations: test material has to be non-porous. Test temperature can affect the test. Many times you have to do it, within a very narrow band of temperatures that something like mag particle is not required. Here we're showing on the left is some of the cleaner, the penetrant, and the developer in cans. It can be sprayed on. Here on the right is showing you some wheels and axle sets that were penetrant tested. Have a little bit of problem. Next thing we'll talk about is what ultrasonic testing. Kind of the new person on the block as far as testing in tank cars is concerned. Ultrasound generation. Ultrasound on a weld is not much unlike what you would receive if you did an ultrasound like in a hospital. It's kind of the same principle. They use what they call a probe or transducer. We call it a transducer, sometimes called a probe. And inside that transducer, there's what they call a piezoelectric element. It's just a crystal that converts electrical energy into mechanical vibrations. These vibrations are ultrasound. You cannot hear them. These things are happening at millions, at like frequencies at 1 million or 2 million cycles per second. These transducers are capable of both transmitting a sound and receiving something coming back. So that's why they call them transducers. And kind of how they work is that inside that transducer, if you apply a small voltage to it, it could be from a battery inside the unit, the UT meter, it will actually make that crystal expand and contract, a million times a second. And these vibrations can be used to put sound into the part. It creates like a mechanical wave. In pulse echo testing, a transducer sends out a pulse of energy, and the same or second transducer listens for reflected energy. It's just kind of like same thing like a principal radar. We'll send out a signal and looking for something to be reflected back. If the reflections occur due to the presence of discontinuities, sound will not go through things like air, ultrasound, because we're talking about frequencies that are really high. So here in this diagram here, we're doing have a transducer on a part, straight beam going down, sound will enter the part, hit the bottom of the plate, and there's like an air to plate interface. The sound will not enter the air, it will actually be reflected back to the transducer. And here on the top right, we see our screen where we have what we call the initial pulse, which is the front surface of our part. Here we have the back surface echo. So we would expect if this plate had no defects in it, that they were detectable, you would want to see no kind of indication or spike on my meter coming back. In this case, we see we have a crack that's looks like mid-wall through the part, and here we get a reflection back. So we would be looking for this area here, and a type of signal would come back. Depending on the size of the signal, if it's a very large signal, you could reject it depending on your procedure. So just like the other method, UT is no different. Ultrasound has a lot of advantages and some limitations. Its advantages, its sensitivity to both surface and subsurface discontinuities. So compared to what some of the methods we already talked about, this is the first method so far that I've talked about where we can look at subsurface defects. We can find defects that are embedded into the part. Depth of penetration, flaw detection, or measurement is superior to other methods. A big advantage of UT, it's only single-sided access is needed when pulse echo testing is used. So sometimes if you want to look at a weld inside a car, like we will show you in X-ray, you only need access to one side, so you can go inside the car and UT a weld without having to have any kind of access to the outside, like if there was a car that had a jacket over it. Really highly accurate for determining reflector's position. Minimal part preparation is required, and it provides instantaneous results. So you don't have to do a lot of calculations, so to speak. It does have some limitations. Surface must be accessible to transmit ultrasound, obviously. The second bullet point is probably the biggest limitation with UT is that the skill and training is more extensive than with some of the other methods. Many times the training can be 2 weeks of training compared to some of the other methods that may be only 3 or 4 days of training. Materials that are rough or irregular shaped, like you see in there, that coupler, there's going to be hard to UT because you got to hook a transducer up to it. So the more complex that part is, it's hard to generate sound into the part. So it's really not good for complex shaped parts and things like castings that are very spongy, because the casting, the big grains in the casting, they tend to have a tendency to dissipate the sound, so it doesn't get a lot of sound coming back to the transducer. We call that a kind of attenuation. So as you can see, so far every method we've talked about, it all depends on what you're testing and things that like that when you're selecting the proper NDT method. Next to last we'll talk about is radiographic testing, sometimes referred to as X-ray. The process of making radiograph is capturing an image on a radiograph or a film. And just like in the hospital, you get an X-ray. Really, industrial radiography is no different than you get an X-ray in a hospital. The only biggest difference is that the source, and we use much more powerful radiation, obviously, to trying to get through a thick part than you would see in a dentist's office or in a hospital. And as far as techniques, X-ray, we kind of divided into two techniques. The one on the left you see here is what they call gamma ray, and that's where they use a live source, something that's like iridium or cobalt-60 that's emitting radiation all the time. A very kind of a safety issue because you have to have proper procedures when using gamma ray. The one on the right is where you just use a machine, an X-ray, where once you turn the machine off, there's no more radiation. So both are very effective. Both are used in the industry, but the one on the left, their gamma ray, requires a little more a safety issue. This is just kind of a diagram that kind of shows you what you do. You have a source here on top. That would be your radiation source. This is your part. Just like in a hospital, you're standing in front of the film. Now, with X-ray, unlike UT, you have to have access to both sides. So you have to put the film on the bottom and the source on the other side. And then you emit radiation to a part. Here we show a picture of the equipment. The equipment is operated to expose the test piece to radiation source, exposing film on the other side of the test piece. So we have here on the left, we're using gamma rays, and this is a tank car with the jacket cut off, out, exposing the exterior of the tank, and I see some heater coils here, and they were going to X-ray this well right here, this tank scene on the left. And this is gamma source where a pill, a little small pill that's radioactive, actually is sent down to this area right here, and it exposes this area to radiation. The one on the right here is an X-ray tube. This is gamma ray on the left, and this is X-ray on the right. This is the bottom of a tank, and they actually just turn this X-ray tube on and expose radiation to the bottom of the part. And in this case, the film was on the inside of the tank. Actually, both. The film was on the inside of the tank. And when you, just like X-ray, you get a latent image, a radiograph that you look at that's captured during exposure. And now if you have areas of defects, and a defect may be something like a crack or something that has less density, a piece of slag, porosity, which is a gas hole, being that the possible defect is less dense, it'll allow more radiation to go through, exposing your film. So what you really look for the most part, is darker areas on your film, indicating you show a radiograph or a film looking for dark spots that could be possibly porosity cracks or things like that. Again, it's a little more of a methodical method than UT. One thing that you're going to see even on the films that you take or an X-ray that you have taken in the hospital is the films are going to have what they call an image quality indicator on the film. Because when you take a picture, a regular picture with a camera, if somebody moves real quick, they will blur in the picture. And you can see that you had a blurry picture. When you deal with film, you're dealing in black and white. So you don't know if you're having a blurred film. So what they do is they put an image quality indicator, and it's just here, this is a plaque type indicator. And it's of a certain thickness, depending on the well thickness. And it has 3 different holes in it, what they call the 1T, the 2T, and the 4T hole, different size holes. And they put this plaque on the part when you X-ray it. So we go to the next slide. This is what they look like under an X-ray. Here we can see that we see the 2T hole. We even can see the 1T hole, the very small hole, showing you a very sharp image. So you may have a procedure that says that you have to show at least the 2T hole, or you have to show a 1T hole being even more sensitive. So it's just kind of an indication of how sensitive your film is in some way. X-ray has a lot of advantages. can be used for many application materials. One thing that people like about X-ray is it's a permanent record. Volumetric or internal structures and conditions can be found. It's a volumetric inspection method, just like UT. Surface finish is not detrimental. Unlike UT, where you had a hard time UT castings, not a problem with X-ray. Here we're kind of showing you a couple radiographs of castings. And here we see our image quality indicators here. And here showing you some possible defects. Limitations, two sides must be accessible. Planar discontinuities are difficult to detect. There is a safety hazard. That's probably the biggest hazard or biggest limitation with X-ray, is that you have to clear out a whole area to do your X-ray, where if you did like an ultrasound, you don't have that issue. And the last thing here let's talk about is thermography. Many times you need to look at the insulation on the car. And here we see on the left is a thermogram of a tank car that's been heated up, and I'll explain those spots here in a second. This thermogram here, these are the jacket spacers. And what you have is you have heat conducted through those jacket spacers, so they show up, and then you can look for a void anywhere around there. And here is an image I took several years ago. I did a thermographic inspection on a car that had some missing insulation on the top of the car, obviously showing red. We heat the inside of the car and look for heat to bleed out. Very good method for looking for insulation. In part two, we'll talk about the application of tank cars to inspection and qualification. Just kind of run through some of these. And depending on what type of NDT method you're going to use, it also depends upon what you're going to be testing. After manufacturing, repair tank cars are required to undergo a periodic inspection. Here's some of the old markings on a car that tells you when this was prior to 1998. I want to skip through that. And here showing you the periodic inspections that are supposed to be done on a car: structural integrity, tank qualification, service equipment, and so on. So periodically you have to do certain inspections in certain areas. I'll skip through this. So we'll talk a little about qualification and maintenance. Definition of qualification is periodic examination based on a written program to verify conformance to federal regulations, AR standards, and customer requirements. Checklist for maintenance program. Do you have a qualified program? Do you use qualified program as intended? And do you have the required drawings? That's something new about having the required drawings to determine what welds are required for inspection. Those are all you would need before you are allowed to proceed on to do the qualification. So then you have all your tools, what I call the tools in your toolbox. You have different types of inspections that are required, and you have a lot of different types of non-destructive testing methods that I could use. And any one of these could be used. So what non-destructive test method is best? This is the $64,000 question. Which NDT method is used to use? Which NDT method to use depends upon several factors. Sometimes they'll ask me, Jim, what's the best method to use? Well, first I say, okay, is there a regulatory or customer requirement for a certain inspection? If there's a federal requirement to do a certain type of method, that's which one you're going to have to choose. What is the criticality of inspections? Not all inspections are as critical as other inspections. What are the likely, where are the likely flaws? And what are the available NDT methods you have in your shop? And then cost. The cost, some of the methods we're talking about can be costly. But when we say cost, that really goes both ways. the cost of the inspection and the cost of using an improper method that you thought was cheaper, and in the long run, you had a problem or issue on a defect you did not find. So those are kind of factors, and I'll get back to this in a second. Let's talk a little bit about structural integrity inspection. Items or locations on the tank car that are susceptible to high stress areas resulting from switching operations, things that happen to those rail cars out in the field. So here we're kind of showing you the bottom of the tank, and these are all areas that can be we call fatigue critical. Head pad to tank welds, a highly critical area. These are areas where you want to maybe take your best methods to use. Attachment welds. Here we're going to see attachment welds to the bottom. This is the bottom of a car, repad on the bottom, and these are all areas of possible inspections. Some of my things are off a little bit, but these are some areas here. Inboard, the seal terminations, these are all areas that are required to be inspected periodically as part of your structural integrity inspection of a rail car. Some typical attachment welds. These are all areas that you're going to require a certain non-destructive test, and depending on the criticality, you may choose one method over the other. Some attached welds too. Tank car failures. Let's talk just briefly about that, and there's something you don't want to see. Categories of failure: distortion of undesirable, undesired deformation, fractures like cracks, corrosion, wear. All those are type of failures that can happen, and it all depends upon the type of part you have, the location on the tank car. We all say the likely candidates of what are going to be areas that you would have to inspect. Some more tank car failure. Here we show on the left is crack on the bottom of tank car, a very big crack. And then on the right is something you don't want to see. Tank, I think that tank's leaking. Here we show you some penetrant on the inside of a car, inside bottom of a tank car. Showing you some cracks here on the right, bottom of a tank car. We have a crack right here. These are some typical items that you're going to find. And I don't want to get too much into the components part of it, but not only do you have to worry about defects on your rail car, but also on some of the components like the wheels and axles. And here on the top right, you can see this crack that happened right here on this wheel. You can see right here in the middle where the crack initiated, and what they call the chevron marks, how the crack kept on growing and growing. So at some point you had a failure. And this is a side cut of the wheel showing you again the fractures happen. But we will kind of run through this. Some likelihood of defect of rails. Some of the more common accidents in our rail industry is because bad rails. Here we show, gentlemen, something I didn't talk about. It's called manual eddy current, using to inspect a rail. But that's something that's going to be used mainly for something on rail, not necessarily tank current. And the last thing I'll talk about, and this is a topic that's becoming a item of concern and something that the regulators are talking about and insisting companies understand the reliability and sensitivity of their non-destructive testing methods and some of the variabilities of inspections. So I'll kind of walk through this for the next couple slides. NDT personnel, how good are my inspectors? How good are my procedures at finding what I would consider critical flaws? And as we talked about earlier, not every part and not every inspection is as critical as the other inspection, depending on the inspection that you're doing. So it brings up that common word we talk about as a probability detection, or what they call the POD. So let's talk a bit about reliability and sensitivity. Probability detection, or PODs, is the likelihood that a flaws of a defined type and dimension and larger can be detected using a specific non-destructive testing system. Here on the left is some tests that we did out at the Transportation Technology Center out in Pueblo, where they had cutouts of tank cutouts and had introduced some flaws in them. The inspectors did not know where the flaws were, did not know how many flaws they were. It was kind of what we call blind test. Inspect it, and if you find a flaw, let me know. And then you can, if you find a flaw, you say, okay, I found one, and if you didn't, then you say you didn't find it. And then you can actually plot this on a graph. On the bottom here on this graph, we have length of cracks. And again, the inspectors don't know where the cracks are. And on the y-axis, or the vertical axis, we have the percent probability that you detected it. And we found some interesting things out when we compared methods on the same plates. So probability detection, and if you talk to any inspector, the inspector is going to say, oh, I found a flaw that was an 1/8 inch wide. I found the smallest flaw. I found this the other day. I found it was the tiniest little crack. I found it. It's really not the smallest flaw that you're going to find. We are really interested in what is the largest flaw that you may miss, and that's where the criticality inspection comes in. So here we plotted with, this is what we call a POD curves. And what we did is we ran side-by-side tests in this instance with 4 non-destructive testing methods with the same inspectors, with the same defects that they didn't know where they were, and ran them through a test using, in other words, we did a visual test, came back and did like a liquid penetrant test, and then say like a magnetic particle test. And then plot the results based off of if they found it, and every crack was of different sizes, and the cracks could be of different sizes. So on the bottom, we have the actual crack length, and this was just for cracks. And then in the top, or the y-axis, we have the probability of them finding it. As you can see, no method was 100%. But for the blue graph curve was visual. As you can see, we'll just take I have here like a 1-inch crack, was 34% success in finding it visually. And you know what that means? It was over 60% of the time you found it was bad. Versus mag particle for the same crack, the mag particle found that same 1-inch crack 76% of the time. Much better than visual. Neither one was 100%. And then, so one good thing about doing a POD curve like this is comparing methods to see which one is better for what flaws I'm really interested in. This visual one here was very eye-opening to some of the people who didn't know non-destructive testing, because visual is not the best for finding flaws compared to the other methods. So reliability and sensitivity continued. Some misconceptions about reliability. It should not be accomplished without knowing what my critical crack size or flaw size is. So before you do a probability detection study, you want to know, okay, what crack, what size crack is really critical in what area. It needs to be performed on a focused inspection, and may not be representative of actual shop field inspection. Because you're doing it where the inspectors kind of knowing they're being watched. But again, they're good for comparing. The POD studies are good for comparing the different NDT methods. POD evaluation results show variability in methods, procedures, and operators. It was kind of an eye-opening for the industry when we started doing some POD studies. Kind of in summary, is non-destructive testing methods. They are tools in the toolbox helping your quality of your inspection. we found out just looking at that no method was 100% effective at finding potential flaws. They all have their advantages and limitations. You always want to take and use your non-destructive testing to its advantage, your method to its advantage, and avoid its limitations. POD studies are a good start, but they may not be indicative of actual inspections. So, summary, thank you, and I hope I haven't talked everybody's head off, but hopefully I've left a little time for some question and answers.
Well, good. Well, Jim, thank you for that. That was an excellent overview and walking through things. So now it's time for everyone to ask questions. We do have plenty of time to do that. You can simply type a question into the question pane on the GoToWebinar sidebar. So let me start with one question that we already have a few queued up anyway, so this is perfect. You at the very beginning, you said non-destructive testing you see it as a risk reducer rather than a cost. Is there a way to be able to kind of measure that risk from a ROI, return on investment perspective, or how should they look at it?
Well, yeah, you obviously have the cost of equipment and training, and that's something that you could put down on a piece of paper, but the risk that's the one that's going to be the hardest. And really, I would say again, what are you looking at? What's the criticality? What is the rail car carrying? Just one accident can be, result in millions of dollars worth of legal fees and fines and things like that. That would just be pale. It would make the cost of your foot pale in comparison to that.
Makes sense. So now one of the questions here is that they state that shippers are required to perform a visual inspection of the car prior to shipment. So is there a good method to easily inspect the jacket for cracks or holes when the jacket is rusty without having to clean the rust off the jacket?
And the question was prior to shipping as a loader?
Yes, as a shipper. It's the shipper's requirement to kind of give that visual inspection. So what, I guess in essence, what's the best way to do that? Or, in this case, it's, do you have to go through, and if you see rust, do you have to get that off the jacket first?
Yeah, again, it goes back to if something like a jacket that's maybe not as obviously as critical as the tank shell itself, you may not have to remove remove rust on the jacket. You may be able to go look for gross defects like that. May not be required. But whatever it is, one thing I would suggest is always using some sort of inspection checklist.
Okay.
Because one thing you see with inspectors that they do miss areas.
Sure. Well, and this kind of goes along with this question just kind of came into at the same time I was asking it. This one is about sandblasting. So, what's the pros and cons of sandblasting an area before testing it?
Yeah, that deals with surface preparation, and every method has different requirements for a surface preparation. And I always say one thing with sandblasting is that if there is a chance, depending on the material, that you could what they call peen the surface, in other words, cover the defect up by smearing the metal. And that's really for more softer metals. But I always say, what is the worst thing trying to look through a bunch of corrosion and things like that, or a nice clean blasted surface. So unless there's some reason, like a soft metal, usually sandblasting, and not so much shot blast, which is a little different, but sandblasting, grit. They have some new methods of cleaning, like that they use like a glass beads, things like that doesn't really peen the surface.
Okay, and that makes sense. When you were showing the curve and you were showing that the probability of missing a crack, and you were looking at they had 3 different measures up there. So this one is talking about this question or that area. So you're saying that there's about an 80% probability of missing a crack that is approximately 1/8 inch to 1/4 inch long, regardless of the method used. I guess that's the question. Is that kind of how they should interpret that, or was that just looking at those 3 methods specifically?
what I showed on the graph was those particular methods on that day with those inspectors. Every probability detection curve or every study will be different than others. The cracks in those curves, the cracks we were looking at, we call kissing cracks, they were extremely tight cracks, very small. They were very hard to find. So we were kind of at a disadvantage with that. And so I would not use that as saying that's typical for all your inspections using all the methods. Those curves will vary depending on what you're looking for and the types of cracks you're looking for. There could be some cracks that are, not kissing cracks that are very easy to find, would drive your POD curves up much better.
Okay, and along with that particular line, so this is as you're kind of talking, so this is just kind of another follow-up on that from somebody. So have you ever found any non-destructive testing method that is higher than 85% effective in finding a flaw?
Boy, that's, yeah, yes.
Okay. And that would be?
What I'm saying is that, again, depending on the type of flaw. Now, if you're looking for flaws that are, very, it's not how long the crack is, it's how wide the crack is. So if you're looking at cracks that are very wide, your probability detection will get over 85. But some of the regulators are requiring something like a 90, what they call 90, 95% effective, and that's hard. That's hard to meet. But yes, you can meet it.
Okay, that's great. So let me keep working my way down here. So what would be a good way for someone to introduce a new non-destructive testing method to their company with no level 2 or 3s on site for training and experience in that method?
First, if the management is bought in and they would want to use that type of non-destructive testing method, they could you just have to go through a process of getting proper training and experience, and then you're required to have some sort of experience hours too involved, and then then you can actually have get the people certified. But you got to start somewhere, so it's not unusual for a company to midstream, to want to use a new method. Okay.
So are there further instructions or guidelines to perform IR inspection on the rail cars that you didn't talk about?
Yeah, because I kind of just briefly went over that. Currently, some of the methods that look for insulation would be just like drilling holes and looking for insulation through a 1-inch or 1/8-inch drilled hole. That's we call that a kind of a poke and pray kind of thing. But if you do like a thermography, a thermographic inspection, it would involve how you're going to heat the car up. These are the things you would have to consider. Are you going to use steam? Are you going to use hot air? What type of camera are you going to use? Cameras, IR cameras, have come down in cost considerably, and this is why it's kind of the new thing on the block, because cameras are now, a good camera can be below $3,000 now, and you get a much better inspection than just drilling a hole looking for an insulation in the jacket.
Understood. Are there statistics of areas of failure on a tank car out there, and is there a database out there that they could use?
That's a good question. I don't know I don't know if I can answer that, but there's information out there. I think you could start with the AAR. I think they probably do have some information out there. I know they had the NAR, which is non-accident release. The NAR program is a good way to start. NAR, I think it's NAR.org.
Perfect. Okay. So if the visual inspection is so low on detection, why use it at all for critical areas in the inspection process? And also, why is POD-like testing not used to determine a specific employee's ability and assign work accordingly?
Well, a real good probability detection study is extremely costly to do it properly. But to get to your first question with visual inspection, it comes out low in probability detecting on certain things, but if you had to inspect a part with one method, visual method is going to probably be your easiest one because you can look at all aspects of the area very quickly. To do a liquid penetrant on, say, on every weld on a tank car would take you months, where a visual inspection can be done in hours. I didn't want to show, what I didn't want to come off is showing the visual as a bad method. I'm just saying that it's a very good method if used properly.
Okay, I have two questions here right in front of me. The first one here is I'm just trying to read through this a little bit for a second. So if POD is used for procedure and qualification, how should a company utilize an NDT procedure to use that information to determine how to approach a possible defect? Are there size, area lists, or so forth to appropriately choose one over the other? I was trying to paraphrase as best I could, so I don't know if that came off correctly or not.
To choose how to do the POD study itself?
Yes.
Yeah, well, what you want to do is look at, you want to make sure it's a focused inspection. So maybe pick out one or two critical areas on your rail car that you want to concentrate on, and then ask what are the orientations of my cracks and possible defects that I could find. You want to narrow your variability down. You want to look at the particular area for a particular defect, even a particular orientation of defect, and then make up flaws representing that defect and that orientation, and then do your POD studies. And make sure that it's a blind test. You want to use several different inspectors. Rule of thumb is at least 3 or more inspectors who run it through and do your studies with the different methods. But I would try to not to use the POD study on just one method. I would use it to compare different methods and to see which one is best and use that method, NDT method, in that area. Perfect.
Final question. I think this is an excellent question. So with the advent of the additive construction, or a lot of times we talk about 3D printing, are there new test methods being developed, or will the current methods be used?
Well, that is a good question. And I didn't go over. There's a lot of. I've been in NDT for over 30 years, and in the last 5 to 10 years, I saw such an increase because of computers and things like that. Such an increase on new methods, new techniques to methods. I like with X-ray. I didn't get into what they call computed radiography. CR, or digital radiography, where if anybody's been a dentist now, you get an X-ray and it goes up on a screen. Those are fabulous new improvements on the methods, and there's actually new methods coming out, Toft and things like this. But yeah, it seems like there's a new technique or new method coming out every year, and new equipment, better equipment.
Perfect. Well, Jim, thank you for that. And as an attendee just typed in here, they said, "You demand." So we appreciate that. That is the end of the Q&A. A reminder that a replay will be available by Friday, November 17th. An email will be sent once it's ready. Please don't hesitate to follow up with Jim or anyone on the AllTranstek or FTR teams if you need anything. Thank you, Jim, for joining us today. And thank you so much for everyone attending. I hope you have a fantastic day and a wonderful Thanksgiving. This concludes our webinar.